Hi guys, it's chapter 3, beginning of chapter 3, talking about electrons. And the first part of the chapter is kind of a review of where electrons are located, and then we'll dive into more specific places where it gets really abstract and more difficult to think about. But moving on. So part A is the simple electronic structure. So basically how many electrons are in different levels of the atom. So the Bohr model is where we basically start, where he has the electron energy levels, and the electron energy levels get bigger, so the number of electrons will grow. And we talked about how the Bohr model is made up in pre-ACE and a little bit last chapter. So quickly, move this. Maximum number of electrons, they grow bigger to get the fourth energy level, and they start going down to get the seventh. That's through experimentation that he figured it out, the maximum number of electrons. You don't have to have that many, but basically the crux of the energy is in that fourth level. So we know there are 7 energy levels because there's 7 periods in the periodic table. And as you become more greater number of energy levels, they get further away from the nucleus. So we know periods are the ones that go across. There's 7 of them. And families are your groups, which are your vertical columns. So they all behave similarly if they're in the same group, where periods have the same energy level. So they're the same circle, we'll say that. Okay. So quickly a review of number of electrons and valence electrons. So calcium is in the 4th energy level, and that's because it's in the 4th period, where in the valence electrons is the group number, which is in the 2nd column, so it has 2 valence electrons. So you quickly go through here. Fluorine is in the 2nd energy level and has 7 valence electrons in group 7. Aluminum is in 3rd energy level and 3rd group. Potassium is in the 4th energy level next to calcium, but it's in group 1, same as hydrogen and lithium. Carbon is in the 2nd with 4 valence electrons. Phosphorus is right below nitrogen, so it has 5 valence electrons. And radon is in the 6th energy level, but it's way out in the noble gases, so it's 8 valence electrons. And hydrogen's 1 and 1. First element on the periodic table, first energy level, 1 valence electron. Alright, so the number is lower, so as you get close to the nucleus, you have less numbers, makes sense. And as you go further out, you have more energy levels. The further you go out in the shell, they're held on less energy, so it takes less energy to pull that electron away, because the nucleus is what's holding the electrons together, because positive and negative. So as you go further away, there's less energy to hold on to those electrons. Energy level 1, period 1 can hold up to 2 electrons. The second one can hold up to 8. The third energy level can hold up to 18. And the 4th energy level up to 32. Alright, so this is where we get more specific of where the electrons are located. Basically just looking at the different energy levels. So you can see here, up here, lithium has 2 in the first energy level with 1 in the second energy level. And neon has 2 in the first energy level, has 8 in the second. Chlorine has 2. So you should see there's a pattern. You can only hold 2 electrons in the first energy level. And chlorine can hold 7 in its valence, so it's 7 at the end. So going by the periodic table, it's really easy to determine how many energy levels they are, and then how many valence electrons based on their column. Lithium, so neon here is number 10. So again, has 2 two electrons in the first shell because of hydrogen, helium, and then the second one you count over has 8 all the way to neon. 8 plus 2 gives you 10. And chlorine over here, third energy level, so that's 3 numbers, 2, 8, 7. Basically, it's just simplifying math. So you know it has 10 electrons from the first 2 shells, 2 and 8. That means it can only hold 7 in the last shell. 7 plus 10 is 17. Okay, you're going to break down again. You're basically adding an electron each time you move over to an element. So notice again, the first shell always has 2 except hydrogen, because it only has one electron. And then you keep adding as you go across. And once you hit 8, it goes to the next energy level of the third. Alright, so you can pause here, but basically you're just going to write the simple electron configuration, how many electrons in each shell, the principal quantum number. So you can pause, write down your answers, and check it out. So sulfur has 286, magnesium 282, fluorine 27, potassium 2881, and carbon 24. So again, just counting how many electrons in each shell. Alright, so first kind of like new topic, ionization energy. Basically, it's just saying it's energy needed to remove an electron. Now the thing it has to be in has to be in gaseous state. So it has to be a gas because that's its most chaotic state. So the more chaotic it is, it's easier to remove that electron. You have to be chaotic. And it has to be 1 mole of that ion. Okay. You can only remove 1 electron at a time, and we'll see that. So here we have calcium. It has 4 energy levels with 2 valence electrons. To remove the electron is basically just like that. You just are removing that electron, taking energy to remove. And that first ionization energy is calcium G gas, yields calcium plus 1 because it removes 1 electron, and it took about 600 kilojoules of energy. Calcium is now plus 1. Now, if it wants to lose another one, which it does because it needs to lose all its valence electrons, it requires more energy. So why does it require more energy? It requires almost twice as much. It's because now, instead of working with it has the same number of protons, it has 1 less electron. So that protons can hold on to its electrons have a little more energy to hold on to its electrons. So it requires more energy to pull away, to remove. Calcium down plus 2. Now, if I took another electron away, now it had its 2 valence electrons, and now it has its 8 in valence electrons. So I take that 1 away. Its third ionization energy. Now, do you think this will be greater or less than ionization energy 2? If you said greater, you're correct, because again, you still have those 20 protons of calcium holding on to even less number of electrons, so it's going to require even more. And that requirement is huge compared to the second ionization energy. So you went from 1100 to almost 5,000 kilojoules. So why does it have such a greater difference? It's because when you remove an electron shell, you have it's stable. You have 8 valence electrons. Its ion is stable. So to require that even more to jump from a different energy level takes a lot more energy. So you can see here a breakdown of ionization energy. It increases almost twice, but then it increases almost 4 times from the second to the third. And you'll see as you continue taking off electrons, the energy is going to get greater and greater. But that big jump between 2 and 3 here is important. So you can see here a table of all these different electrons removed. And as you go across, let's look at carbon. Carbon goes from 1,000, 2,300, 4,600, 6,000, and then a big jump, almost 38,000 kilojoules of energy. Okay, so notice it has 4 valence electrons. So once it removes all its valence electrons, it takes a huge jump to remove its next electron. And you can see that with, let's say, oxygen. Oxygen has 6 valence electrons, so you look at the 6, and then go to your next one, big jump, 13,000 to 71,000. So again, we know that lost all valence electrons at 6. All right, so let's look at, again, this difference between ionization 1 and ionization 2 versus ionization 2 and ionization 3. So again, between 1 and 2 is only about 600 kilojoules of energy to remove the difference between the two. But again, you look at between 2 and 3, it took 3,700 kilojoules of energy. So a tremendous amount of difference. And that's because of its jump after removing all its valence electrons. You now have a stable shell energy level with its 8 valence electrons. So the closer the electrons removed to the nucleus, the more energy required to remove it. Okay, that makes a lot of sense because once you start removing electrons, the electron radius, or sorry, the atomic radius begins shrinking because the pull of those protons. Its protons aren't changing. There's still 20 protons there. Now it's less electrons, so the force between the protons and electrons is even greater. All right, so we look at lithium. So lithium, removing 1 electron, requires about 500 kilojoules of energy. Bye-bye. Now it has 2 valence electrons, and now it's empty shell, or its first shell is gone. So you can see it's going to be a big jump between first and second. Between it's 500 to 7,300, so it's a huge jump, 14 times greater to remove that electron. So as a new electron is removed, what happens to ionization energy? So ionization energy is going to increase no matter what. So as you remove more and more electrons from that atom, it gets harder and harder to remove that other electron from its atom, its ion, because of the proton attractive force between in the nucleus is getting greater and greater. There are huge jumps between successive ionization energies. That's when it removes its valence electrons, and then it has a new shell, new energy level of full electrons. So that is why you have a big jump at those levels. So let's look at nitrogen for a second. So nitrogen has 5 valence electrons, and then has 2 in the inner shell. It's in group 2, so it has 2 energy levels. So energy, nitrogen has a 2,5 configuration. Okay, these are its energy level, ionization energies. So you can know it's all increasing. Okay, just like any other ionization energy, but no big jumps here. It's the same shell. Yes, it's increasing, but again, it's within the still thousands. So 1,400, 2,800, 4,500. Okay, it's increasing pretty regularly. Okay, but then the 6th and 7th have huge jumps. But between the two is, again, no big jumps because they're at the same energy level, same shell. So the biggest jump is between 5 and 6. It goes from just under 10,000 to 53,000. So it's going to have, that's where you see the difference in the shells. So when you see a big jump, that means it removed all its valence electrons, and then it has a new shell where electrons are located. So you can see it's 6 times greater from 5 to 6. All right, here's your homework question. You finish this on Teams. You're going to write the ionization energies of calcium, the third ionization energy of potassium, the second ionization energy of lithium, and the fifth ionization energy of sulfur. All right, factors that influence ionization energy. So the size of the nuclear charge, as the atomic number increases, ionization energy increases. So the atomic number, the number of protons, is going to hold on to electrons more. So it's going to take more energy to remove, which makes sense. More protons means more charge. So more protons within the same shell will cause a greater attraction for the electrons. The distance, so the further you are from the nucleus, it takes less energy. That's why the ionization energies of, as you go down the periodic table, decrease, because there's more distance. They call that shielding. So as you more energy shells, the protons are further away from the outer electrons, therefore they're going to be easier to remove. And that's what the inner electrons do. They cause a shielding effect, almost like blockers in football. The electron shells increases because they're going to cause like a shielding effect from the nucleus to the outer electrons. And with greater distance, other electrons get in the way of that attractive force. Therefore, the outer electrons are easy to remove. You can see in this graph, this is sodium. It goes, the first electron is right here, and then the second is a big jump. That's because sodium is in the first group, has one valence electron. So once you remove that one electron, it's going to have a big jump, and then some minor, just little jumps here, and then you get another big jump. Okay, if you count here, 1, 2, 3, 4, 5, 6, 7, 8, because once you remove that one electron from the first, its third energy level, you have 8 electrons now in the second energy level, and then you see a big jump because now you're in the first energy level with 2 electrons. So we know this is a 281 because it has 2 in the first, 8 in the second, and then 1 at the end. All right, so we have plus 11, so that means we have sodium. So you can see here, sodium has 1 removed electron in the outer shell. It's easily removed. And then once you remove that 1 electron from the shell, you're going to have 8 valence electrons, and it becomes harder and harder and more difficult to remove. And the most difficult to remove is the last 2, which is closest to the nucleus. All right, so let's look at some examples again of energy levels, energy shells, and ionization energies. Here we have boron. Okay, so the question is, why is there a large increase between the third and fourth energy levels? So you can see between 3 and 4, it goes from 3,600 to 25,000. Huge jump. Okay, so you can see here, boron has 3 valence electrons. Okay, so once you remove these 3 valence electrons, you are now into a new energy shell, the first one. So that's why there's a big jump between 3 and 4. So you remove 1, remove 2, remove 3, then you have a new shell. That's proof that boron has 3 valence electrons because it takes so much energy to remove that 4th electron because it's in the new shell. 7 times much more. Okay. So explain how these figures confirm the electron structure is 2, 3. So once you reach a 1, you need 5 electrons. It has 5 electrons, so we know that's true. So why is it proved 2, 3? Because if you're working backwards or forwards, if you go backwards, you see a big jump of decrease between the 4th and 3rd. So you know there's 2 electrons in this energy level. You know there's 3 in this one. And it has to be 3 in the last one because the first energy, ionization energy, is the lowest. So that confirms it's a 2-3. All right, which group in this periodic table does the element belong to? So looking at this information of the ionization energies of this element, we have to find out what group it's in. Basically, we have to figure out where there's the biggest jump between ionization energies. So you can see between 1 and 2, it's all pretty much standard. It goes 1,000, 2,000, 3,000, 4,000, 7,000, 8,000, and then you get to 27,000. Boom. So that's a pretty big jump. Let's see if there's anything else that caught our eye. All relatively pretty small jumps. Okay. So we can see the biggest jump between 6 and 7. That means the 6 one removed, it took 6 of them to remove from the last shell. So that means it has to be in group 6. So this could be oxygen, it could be sulfur, it can't be oxygen because oxygen only has 8, but it could be sulfur, something in that group. All right, so last question for this section. Checkout number 4. We have 6 ionization energies of this element. And you're going to determine which group this element belongs to in the periodic table, and explain using the data of your reasoning. And this is done also in teams. Just click on the assignment for Chapter 3, Part A, and type in your answer, and then submit it. All right, so if you have any other questions or any clarifications, you can always ask that in class. And get ready for Part B.